In the previous video, we developed an analogy between the motion of a mass on a spring and the motion of a mass tracing out a circle. We found that the horizontal coordinates of the circling mass and the mass on the spring could be made to coincide exactly with each other if the angular velocity of the circling mass was equal to the square root of the spring constant divided by the mass attached to the spring. In this video, we're going to try and get a little bit more information out of this analogy. In particular, we're going to ask, what is the period of motion for the mass attached to the end of the spring? So recall that period refers to the time needed for one complete cycle of motion. So for the mass on the spring, the period of motion would be the time needed to start over here, then go all the way to the left and all the way back to the right. The time needed for that would be one period. And for the circling mass, the period would be the time needed to complete one circle. We want to see if we can use this result that we got from the previous video to work out an expression for the period of the mass on the spring. We're going to do this by going back to that circular motion analogy that was developed in the previous video. Let's look at that circling mass. The angular velocity of that circling mass would be the angle delta theta that it sweeps out in some time interval divided by the time interval. So to get the angular velocity for the circling mass, let's just think about that circling mass making exactly one circle. When the circling mass makes exactly one circle, then the angle it sweeps out is 2 pi, and the time it takes to make that circle is the period. This tells us that the angular velocity of the circling mass is 2 pi divided by the period. However, since we are assuming that the motions of the circling mass and the motion of the mass on the spring match up, then this period here would be the period for both the circling mass and the mass on the spring. So let's solve now for the period. So we're going to take the period from the denominator on the right up to the numerator on the left, and then omega from the numerator on the left to the denominator on the right. So they switch places, and we get period equals 2 pi over omega. So we're almost there. All we have to do now is just take this expression for omega that we got in the previous video, and then we have that the period of the motion for both the circling mass and the mass on the spring is 2 pi divided by the square root of spring constant over mass. So now let's take this expression in the denominator and flip it up into the numerator. And now we have our expression for the period of a mass oscillating at the end of a spring. It is 2 pi times the square root of the mass divided by the spring constant. So we have then that the period of a mass m oscillating on a spring with spring constant k is 2 pi times the square root of the mass over the spring constant. Before closing out the video, I'd like to introduce you to some terminology. In an earlier video, I introduced you to the idea of frequency. The frequency of an oscillator is 1 divided by the period of the oscillator. With that in mind, notice that the angular velocity can be written as 2 pi times 1 over the period. What that means is that the angular velocity of our circling mass from before is equal to 2 pi times the oscillation frequency of the mass attached to the end of the spring. Because of this close connection between omega and the frequency of the oscillator, we're going to introduce a new term. We're going to say that an oscillator with frequency f has an angular frequency omega, where the relation between those is that the angular frequency omega is equal to 2 pi times the regular frequency f. Let's put all of this together for the problem of a mass m oscillating on a spring with spring constant K. First, we would have the period of the motion. As we saw in this video, the period of the motion would be 2 pi times the square root of the mass divided by the spring constant. Then we would have what we call the angular frequency of the motion. The angular frequency of the motion is denoted by omega and is equal to the square root of the spring constant divided by the mass. And finally, and we don't actually use this very often, but we can write down an expression for the regular frequency of the mass oscillating on the spring. Now from here, that regular frequency would be equal to the angular frequency divided by 2 pi, or in other words, the regular frequency would be 1 over 2 pi times the square root of the spring constant divided by the mass. In the next video, we're going to do a fairly simple example, which basically will involve taking these formulas and using them along with some numerical values.